So we've learned about how to balance chemical reactions. Again, I do it by the counting method. There's an algebraic method as well. If you would like that, just let me know and I can get you a link to it that was prepared by a former student of mine. I just prefer to do it by the counting method. Let's go ahead and practice some more examples. First up, we have some cobalt-3 oxide reacting with carbon, producing cobalt and CO2. Be careful with cobalt because, again, they look very similar. C little queso, C bigger O. Cobalt versus carbon monoxide. Make sure you're writing the right one, okay? This is one of the cases where it's very specific that you are writing that second letter lowercase when it's for that element, because cobalt and carbon monoxide are very different things. First thing I'm going to do is I'm going to write underneath it CO, O, and C. I'm going to match that on the other side. CO first, O second, and C third. Now I'm going to write down how many elements I have of each species currently on that side of the reaction. On my reactant side, I currently have 2 cobalts, 3 oxygens, and 1 carbon. On my product side, I currently have 1 cobalt, 2 oxygen, and 1 carbon. I could go ahead and just balance my cobalt first and say it will times 2, but the thing is my oxygen, the 3-to-2 ratio, that's going to have to be fixed. The moment I fix my oxygen, it's going to mess up everything else in the reaction. So I'm going to go ahead and fix that oxygen first. Doesn't really matter. You could fix the cobalt first, but then you're going to have to fix it again. For oxygen, to get this to a common thing, I'm going to multiply this by 2 and this by 3, giving me 6 on each side. So this will be a 3 CO2 here and 2 CO2O3 here. When I do that, that multiplies my cobalt by 2, giving me 4 cobalt, and multiplies this carbon by 3, giving me 3 carbon. Now I can go ahead and fix my cobalt and my carbon. Times this by 4, giving me 4 cobalt here. Times this by 3, giving me 3 carbon here. And just to rewrite this so you guys can see it clearly, now we'd have 2 COO3, 3 carbon, 4 CO, and 3 CO2. Let's check everything. Oops. It would help if I wrote the right formula. I apologize. 1 second. There should be a 2 there. Wrong direction. 1 sec. I apologize. There we go. That looks better. I now have 4 cobalt on my reactant side and 4 cobalt on my product side, 6 oxygen on my reactant side and 6 oxygen on my product side, 3 carbon on my reactant side and 3 carbon on my product side. And the reaction is balanced. The next example I have down here, strontium chloride reacting with lithium phosphate, forming strontium phosphate and lithium chloride. I'm using this example very specifically because I have a polyatomic here that is not breaking apart. Got strontium, chloride, lithium, and phosphate. Strontium, chloride, lithium, and phosphate. I could go ahead and split up that phosphate and put P and O. That is totally fine, but I don't have to. I see the polyatomic staying together. If a polyatomic stays together, balance it as a single unit. It's just one less step for you. My strontium right now I have 1, chloride 2, lithium 3, and phosphate 1. On the product side, I have 3 strontium, 1 chloride, 1 lithium, and 2 phosphates. So it doesn't really matter which one I go ahead and balance first. I guess let's just start with strontium. I'm going to say times 3 here, giving me 3 strontium here, putting a 3 out front here, keep that as times 1, 3 strontium on each side. When I did that though to the reactant side, when I multiplied that strontium chloride by 3, that means I have multiplied this chloride by 3 as well, giving this a 6. I need to put a 6 in front of my lithium chloride. That gives me 6 chlorides on this side. That also gives me 6 lithiums on this side. Now I need 6 lithiums on my reactant side. So I'm going to multiply this by 2, giving me 6 lithiums on my reactant side. That multiplies my phosphate by 2, which perfectly matches what I have on my product side. Let's go ahead and rewrite that. 3 strontium chlorides, 2 lithium phosphate, gotta put the 3 under there, I apologize. It's really hard for me to write on the bottom of the screen. Let's see. 1 strontium phosphate and 6 lithium chloride. Let's make sure it's balanced. And again, when you're rebalancing these, you should be writing the phases in as well. So you should have included the solid, gas, and the aqueous, solid, aqueous. Again, aqueous just meaning it was dissolved in water. But let's check. I have 3 strontium on my reactant side, 3 strontium on my product side, 6 chloride on my reactant side, 6 chloride on my product side, 6 lithium on my reactant side, 6 lithium on my product side, and 2 phosphate on the reactant side, 2 phosphate on the product side. So we're good. Now the last example on this slide, NH42Cr2O7, solid, giving me Cr2O3 and 2 in H2O. This is known as a decomposition reaction. We're going to talk a lot more about reaction predicting in the next chapter. But if you are starting with one reactant and forming multiple products, you are decomposing a sample. And what's pictured down here is what actually happens. This picture here is the ammonium dichromate. NH42Cr07 is ammonium dichromate. We burn that, it decomposes, forming Cr2O3 and 2 in H2O. In this case, though, my polyatomic is not staying together. Because it's not staying together, I'm going to have to write down each species. Nitrogen, hydrogen, chromium, oxygen. Nitrogen, hydrogen, chromium, and oxygen. On the reactant side, I have 1 nitrogen here, but there's a 2 here, meaning I actually have 2 ammoniums, which gives me 2 nitrogens. I have 4 times 2, or 8 hydrogens. I have 2 chromium and 7 oxygen. On the product side, 2 chromium. Here I have 3 oxygen, 2 nitrogen, 2 hydrogen, plus 1 oxygen. My nitrogens match, my chromiums match. My hydrogen does not match. So I'm going to go ahead and say, okay, multiply this by 4, giving me 8 hydrogen. When I did that, that multiplied this oxygen, the specific oxygen here by 4, giving me 3 plus 4, overall 7, and now my oxygen matches as well. So to balance this equation, I only needed to put a 4 in front of that H2O. But I needed to pay attention that my polyatomic, ammonium in this case, and dichromate, both ammonium and dichromate, did break down and did not stay together as a polyatomic. So it's not always possible to keep your polyatomics together. If it is possible, I recommend it. It's just easier. But if it's not possible, you will have to split them apart. The one type of reaction you are responsible for right now. The rest of them you will be responsible for in the coming chapters. But right now, you are going to be responsible for combustion reaction. A combustion reaction is when I burned something in the presence of oxygen to form CO2 and water. Most specifically, right now, you are responsible for burning a hydrocarbon. Hydrocarbon means, just like it sounds, hydro, hydrogen, carbon, carbon, a compound containing only carbon and hydrogen, or a compound containing hydrogen, carbons, and oxygens. These are the ones you are responsible for right now. If you have a hydrocarbon or a compound containing hydrogens, carbons, and oxygens, if I say it undergoes complete combustion, it means it burns in the presence of oxygen to form CO2 and water. So you have to know that the other reactant is oxygen and the 2 products are CO2 and water. Complete combustion, the products are CO2 and water. Now, you will hear about incomplete combustion. Incomplete combustion is when we don't have enough oxygen present. There is an insufficient supply of oxygen, so the products will actually be CO and water. I will not ask you to balance that one, but I want you aware that that's what's happening. We want to encourage complete combustion so that we actually are producing CO2, not CO. CO2 is something we can deal with as humans, CO is not. Again, complete combustion is what you're responsible for, but you should at least be aware of what incomplete combustion is. I won't ask you to balance incomplete combustion. If I did, I would tell you these are the products. If I'm expecting complete combustion, I'm not telling you the products. I'm going to say this undergoes complete combustion. and I expect you to know that means it reacted with O2 to form CO2 and water. Let's work an example. What if I gave you the compound in words? How would you work through this? If I said aluminum metal reacts with air to produce a white powdery compound, aluminum oxide, what I want you to ask first is ask yourself, what is reacting? Well, it tells me aluminum metal reacts with air. Aluminum metal, pretty straightforward, Al, solid. Al is the symbol for aluminum. But reacting with air means reacting with O2. Why are we not saying reacting with O2? I don't know. I didn't make it up. But when I say reacting with air, I really mean it's reacting with oxygen. Remember, oxygen is one of your diatomics. You need to remember your diatomic and polyatomic elements. So your diatomics, H2, N2, O2, F2, Cl2, Br2, I2. You got 7 of those. And your polyatomic elements, P4, As4, S8, Se8. So if I say something reacts with phosphorus, I mean P4. If I say it reacts with selenium, I mean Se8. What is being produced? Ask yourself that question next. What is being produced? It says aluminum oxide. What are the forms of each reactant and product? Meaning, are they solid, gas, liquid, or aqueous phase? Well, aluminum metal, all metals are solid except mercury at room temperature, so we can safely assume aluminum is a metal. We know oxygen is what we're breathing in, so oxygen is going to be a gas. And then it says here, a white powdery compound. White and powdery to me means solid, so I know that my aluminum oxide will be a solid. Write the correct formulas for each species. Al plus O2 giving me Al2O3. I have to recognize aluminum oxide. I know alumina is always a 3+ charge. I know oxide is always a -2 charge. So that means I have to have 2 aluminums for every 3 oxygen to charge balance that ionic species. Write the correct phases for each species, my solid, my gas, my solid, and then balance my equation. I see here I have 1 aluminum to 2 aluminum and 2 oxygen to 3 oxygen. I'm going to balance my oxygens first, putting a 3 in front of this and a 2 in front of this, which causes me to have to put a 4 in front of the aluminum here to balance out my reaction. Let's work a couple examples. Write the complete balanced equation for the complete combustion of ethane, C2H6, and oxygen. Now, this slide is actually giving you more information than I would probably give you. I could just say, write the complete balanced equation for the combustion or complete combustion of ethane, C2H6, not even say in oxygen. You have to know that oxygen is the other reactant. So, C2H6 plus O2 giving me CO2 and water. I'm going to look at this, and I've got carbon, hydrogen, oxygen, carbon, hydrogen, I'm going to put over here oxygen. 2 carbon, 6 hydrogen, 2 oxygen. On this side, 1 carbon, 2 hydrogen, and 2 + 1 oxygen. I'm going to balance my carbons and hydrogens first. Let's go ahead and balance my hydrogen. So that's going to be +3 here, overall 6, or times 3. 3 times that H2 giving me 6 hydrogens. That did change my oxygen here. So now I have 2 + 3, giving me 5 oxygens. Let's balance my carbons. I have 2 carbon on one side, 2 carbon on the other. I'm going to put a 2 in front of the CO2. That has changed this oxygen to a 4. I now have 4 + 3, or 7 oxygen. I have 7 versus 2. The 7 versus 2 thing is kind of hard to balance, and I can play with this back and forth and get it to balance, or I can do what I call a shortcut. The shortcut is where you take the bigger number on the product side and put it as a fraction over the smaller number that's on the reactant side. This will happen not always, but sometimes when you have a diatomic on one side. If you have an odd number on one side, on the product side, and then you have the number 2 for your diatomic on the even side, it's easiest to make a fraction. We have to get rid of the fraction, but it's a temporary thing. I can say 7/2 O2. 7 halves, 7 divided by 2, is the same as 3.5. 3.5 times 2 is 7. This balances out my reaction. It gives me 7 oxygens on each side. The thing is, we cannot leave a reaction in fractional form. Mathematically, it doesn't matter if we're calculating, if we're doing stoichiometry, which will be which is later in this chapter. But it's not common practice for a Gen Chem class to leave these in fractional form. We need whole numbers. There's only a very specific type of equation where you allow fractional forms, and that is not this. That is a formation reaction. There's a specific reason for it. So I'm not allowed to leave this in fractional form. What I'm going to do, now that I have it in fractional form, and it is in fact balanced, is I'm going to multiply through the whole reaction by 2 to undo this factor. 2 C2H6, 7 O2, 4 CO2, and 6 H2O. Let me move this down so we can see it, and then we'll check it. Now I have 4 carbon on each side. I have 12 hydrogen. I didn't read that right. 12 hydrogen on each side, and oxygen, 14 oxygen on each side. So my 4 carbon, my 12 hydrogen, 14 oxygen. 4 carbon, 12 hydrogen, 8 plus 6, my 14 oxygen. So again, I can't leave this in fractional form, but I can use the fraction as an intermediate step to balance this out faster. You don't always have to do this, but sometimes it will help when you're doing, especially combustion reactions, but reactions where you have this diatomic on one side that can kind of throw things off for you. What about this next example? When the balanced equation for the complete combustion of ethanol, CH3CH2OH, is written using the smallest whole number coefficients, what is the coefficient on oxygen? The way ethanol is written here is the organic form. It's telling me how the compound's actually connected. That's not exactly the most helpful way when balancing equations, though. So if you're good at it, go for it, leave it as is. But if you're getting a little mixed up on it, I recommend combining the elements. If I look at that, I've got C2H6O. CH3CH2OH means I have 2 carbons, 6 hydrogens, and 1 oxygen. I'm going to go ahead and combine them so that I don't miss it when I'm actually balancing this out. Ethanol is a liquid. Combustion means react with O2 to form CO2 and water. Now I'm going to count up what I have: my carbons, my hydrogens, my oxygens, my carbons, my hydrogens, my oxygens. Reactant side, I have 2 carbon, 6 hydrogen, and 1 plus 2, or 3 oxygen. Product side, 1 carbon, 2 hydrogens, 2 plus 1, or 3 oxygens. I'm going to balance my carbons first, so times 2 here gives me 2 carbons on this side. When I do that, that changes my oxygen here. I no longer have 2 there, I have a 4 for the oxygen here. Next up, I'm going to balance my hydrogens. I have 6 hydrogen on my reactant side. I'm going to get 6 hydrogen on my product side by putting a 3 in front of my water. That changes my oxygens here. That gives me 3 oxygens here. Overall, 7 on this side. My carbons are balanced, my hydrogens are balanced, but now I have this oxygen 3:7 ratio. I don't need a fraction this time, though, because my oxygen is split across 2 different atoms. What I can easily do here is I can easily put a 3 in front of the O2 here, which changes this to a 6, which changes this to a 7. And so to answer the question, the actual question here is, what is the coefficient on oxygen? The coefficient on oxygen is just 3. There is 7 oxygens on each side of the reaction, 7 individual oxygen atoms on each side of the reaction, but there is only 3 molecules of oxygen on the reactant side. So on the coefficient on oxygen itself, that means molecular oxygen, the diatomic, the coefficient is 3. And 2 more examples. Write the balanced equation for the reaction of solid potassium chlorate decomposing to form solid potassium chloride and oxygen gas. So let's see what we got going on here. Solid potassium chlorate. Well, I know potassium is K plus, and I know chlorate is ClO3 minus, so that must just be KClO3. It tells me it's a solid, and it tells me it's decomposing, which means it is the only reactant. It forms solid potassium chloride. I know potassium is K plus, chloride is a -1. So again, potassium, group 1, alkali metal. Alkali metals only form a +1 charge. And I know chloride is a halogen. All halogens, group 17, will form a -1 charge. Chlorate is one of the polyatomics I have memorized. Remember the pattern: chlorate, ClO3 minus, perchlorate, ClO4 minus, 8 to ite, chlorite is ClO2 minus, and if I lose one more oxygen, I become hypochlorite. This gives me KCl, solid, and oxygen gas, so O2 gas. Let's go ahead and balance this out. I've got 1 potassium on each side, 1 chlorine on each side, but I have 3 oxygen on my reactant side and 2 oxygen on my product side. To balance it out, I'm going to put a 2 in front of the potassium chlorate and a 3 in front of the oxygen. Now my oxygens are balanced, but now my potassium and chloride are not balanced. I have 2 potassiums on my reactant side. I need 2 potassium on my product side. Now I have 2 potassiums on each side, 2 chlorines on each side, and overall 6 oxygens on each side, and the reaction is in fact balanced. And the last example, give the balanced equation for solid iron 3 sulfide. So let's see, iron 3 is Fe3 plus, sulfide is from sulfur, the ion of sulfur, so S2 minus, that will give me Fe2, S3, so Fe2, S3, it is a solid. Reacting with, that means plus sign, gaseous hydrogen chloride. Now hydrogen chloride, technically by naming rules we should call that hydrogen monochloride, but we don't because we don't always follow the naming conventions. And so hydrogen chloride does mean HCl, HCl gas phase. To form solid iron 3 chloride, so again iron 3 means Fe3 plus, chloride is a Cl minus, so that's going to give me FeCl3. To form means your arrow. FeCl3, and that is a solid phase. And hydrogen sulfide gas. Again, this one is not the most helpful naming, the way we do this, but I know sulfide is S2 minus. And in order to make it hydrogen, I have to make this neutral. I need 2 of these to make this neutral. So this will be H2S in the gas phase. So let's look at the balancing. I've got 2 iron on my reactant side and 1 iron on my product side. Let's go ahead and put a 2 there to balance out my irons. I've got 3 sulfur on my reactant side, and I've got 1 sulfur on my product side. And go put ahead and put a 3 in front of my H2S to make the sulfurs balance. Now I've got 1 hydrogen on my reactant side, but 6 hydrogen on my product side. I'm going to put a 6 in front of the HCl. I now have 6 chlorides on my reactant side and 6 chlorides on my product side, and the reaction is completely balanced. So we have successfully balanced both of these reactions.